All right. Well, I'm going to get started. Okay. Did remember to record this. Okay. First of all, just to give you a little general knowledge about the assessment that's going to be on C Day this week. It's pretty much a normal test. So it's going to be 10 multiple choice, not use a calculator. So we're not going to give you a break on that one. And one short answer. Okay. And the short answer, I had to say, I think it reminds me very much of the example free response that's on page 30. Page 30 in your binder. It's on the back side of the last page of the NoCo Practice. I haven't posted the key on Schoology just yet, but I will. I think that's a pretty great question. So again, that was page 30, the AP free response question from the textbook. Okay, so any general questions about what the test is going to be like? And again, you guys, guess what? From my perspective, I'm sitting here in my kitchen and I'm looking at a lot of black screens, which is totally fine, but I'm not getting that much feedback. So if something is wrong, please tell me. Okay, if you can't hear me, I don't know if I say something wrong, please just type it in the chat. Okay, and if you see me looking off to the side like I am right now, that's because I have the chat open in another window. Okay, so I'm going to keep checking that. Also, with the chat, unfortunately, since I'm using two screens, it's like there's two me's. So if you're okay with it, I would suggest not direct messaging me because that's going to go to this main computer and I'm not checking the chats on that. Okay, I'm just checking the chats that will go to everyone. Okay, if you don't mind. Okay, if you have something that you really want to go to me personally, you can text it to me. I got my phone here. Okay, I'll try to check that. But if it's okay, just try to make it like a public chat. Okay, not to just me. All right. Okay. So let's see. First of all, let's start with explain the difference between Bronsted-Lowry, Lewis, and Arrhenius. We got that one. Real quickly, though, someone asked about worksheet A. And gosh, I guess you're right. Maybe we didn't put that in the binders. You know what? You don't need it. Okay. If there's a worksheet A to be done, I think there's plenty of other practice. So I know on the calendar, like I said, page 30 is really good practice. The other ones that are really good practice was page 17. Let me make sure that's right. Yep, page 17 was some extra practice, and there's one more. It was called Getting Buffed with Buffers. Or no, sorry, pH Fun. pH Fun. There it is. That was page 25. So if you're looking for some extra things to do, again, that was page 17, that was page 30, and that was page 25. Okay, my favorite is page 30. So I think that's plenty of practice. Do not even worry about what she said. Okay. Do I see any more snowvid days in the future? I'll be honest with you guys. I don't think we're going to get another snowvid day. I don't think we're going to go remote either, which I think is good news. Okay, so that's my opinion, but we'll see. I'm always wrong. Ms. Schneider is a much better authority at that. Okay, so I see a request for some no-calc practice like number 12, which is a great one. So I'll definitely go with that. All right, so let's officially get started. I'm going to go ahead and where did my, hold on a second here. Share screen. Sorry, I lost my whiteboard for a minute there. All right, you guys should see my whiteboard. Let's get rolling here. Okay, so the first question said these definitions. So there's basically Arrhenius, there's Lewis, and there's Bronsted-Lowry acid and base. Folks, I am telling you, the only thing you really need to know is probably the Bronsted-Lowry acids and bases. They are basically proton, which is really just H+ donator. That's basically an acid, proton or H+ acceptor. That's basically a base. Okay. So, but guess what? The definition we've been using since day one, that acids donate and bases accept, has been the Bronsted-Lowry acid base definition. Okay. Arrhenius is a little bit different. I'm not even sure I'm spelling that right. I think so. Arrhenius is basically acids in water produce H+. Okay, and bases in water produce OH-. Okay, and bottom line is it's really the same definition. It's the net outcome of Bronsted, Lowry, acid, and base. The only difference there is Arrhenius is specific to aqueous solutions. Whatever, okay, that's no big deal. I don't think I'm ever going to ask you any specific questions about the Arrhenius definition. Okay, now perhaps, you know, on OWL, I let some Lewis acid-base questions kind of sneak in. And really what they consider this previous knowledge. So I don't know, I guess the AP College Board thought you guys would learn that already. And I know it was new to us, but bottom line is it's not that hard, okay? So a Lewis, and I'll let some more people in. A Lewis acid is a, what do I want to say? Is a lone pair acceptor. Okay, and a Lewis base is a lone pair. You know what? And I just said that wrong. Lone pair donator. Okay, and base is a lone pair. Hold on, give me 1 second. I got too many things going on right now. Goodness, I'm sorry. Yeah, let me just let some people in. Okay, lone pair acceptor, lone pair donator. Okay, now donator. Now we're rocking and rolling. So I'll give you guys a great example. So you know how we talk about like aluminum +3, actually. Hold on a second. Let me erase that real quick. I'll give you guys a real good example. So like when we talk about copper 2+, okay, it's, you know, a metal, highly charged metal, okay? And guess what? It gets hydrated, okay, with water molecules, right? Okay, we talked about that hydration process. Okay, well, the bottom line is why does that happen? Okay, so copper 2+, it actually accepts. Trying to switch colors here. Okay, basically a bond is created between the copper 2+ and the lone pair between the O. So copper 2+ is a lone pair acceptor. Okay, so that makes this guy a Lewis acid. And guess what? The water here, it has that lone pair and it's donating them. So that's makes the water in this case a Lewis base. So, you know, bottom line is you kind of knew that already. Okay, is that one of the characteristics of bases in general, whether it's Bronsted, Lowry base or a Lewis base, is that the key feature of a base is that somehow, some way, like here's your classic base, it has that lone pair, okay? So these definitions definitely overlap, but I think what I would want you guys to remember from this is the Lewis base is something that has a lone pair on the central atom, okay? And that guy right there is going to be donated to the acid and create the connection. That's it. That's all you really need to know. In terms of Lewis acids, well, gosh, they're lone pair acceptors. So they have to have space to accept a lone pair. So I don't want to dwell on it too much because I don't think, well, I know you're not going to see it on C day, okay? Whether you see it on the AP exam or something like that, it's possible, okay? But I think somewhat unlikely. But I'll give you guys one quick example, okay? Like this is a really great example. If you had something like BH3, okay, reacting with NH3, okay? I didn't draw this with the best orientation, but the bottom line is if these two reacted, I bet you could figure out which one was the Lewis acid and you could figure out which one was the Lewis base, okay? So when you look at these, you're like, oh, let's see here. Well, that looks like a lone pair, okay? So, and this is a classic base. You knew it to be a base anyway. And BH3, you might say to yourself, that's not like a traditional acid, you know, but you know what? It has 1, 2, 3 bonds. And you know, octet rule says that it could hold a 4th bond. So could you see that this might be like a match made in heaven? So what you'd see happen here is, you know, that BH3, I'm kind of changing the orientation around just a little bit. It could connect with this lone pair that would create the bond that's right there. Okay, and then you just have the rest of the molecule, the NH3. Okay, so that's a classic Lewis acid-base reaction. It's a little bit different from like the acid-base reactions we've been talking about. And I would say that's what you need to know. Okay, so Lewis acid, lone pair acceptor, Lewis base, lone pair donator. Okay. All right. Whew. Let's see what else we got. I'm going to look back at the chat. I think I answered that question pretty sufficiently. Let's see here. So, let's see. I see a request to go over some NoCo Practice, like number 12 on the, so I'll do that. How is the pH scale affected by changes in temp? I can talk about that. What did OWL mean by major species, and will we have to do anything with that? The test and NoCo question number 19. Okay, so let's see if we could do that. I hope you guys are doing all right. I'm looking at the chat one more time to make sure no one's telling me like I got ants on my ears or anything like that. Okay, number 12 on the NoCo Practice. You know what? I'm gonna give you guys a better one. Okay, so where is number 12? Ooh, yes. Okay, just kidding. Number 12. That was the one I was thinking of. That's a hard one. Okay, and you know, whoever asked that question, valid point. That was kind of tough to do without a calculator, but I'll give you guys some tips. So for number 12, it says the Kb value for H PO42 minus was 1.6 times 10 to the negative 7th. Okay. And it says which of these species would have a Ka value of 6.2 times 10 to the negative 8. Okay. And that's a Ka value. Okay. Times 10, 6.2 times 10 to the negative 8. Okay. So what jumps out to me is that we're dealing with a diprotic acid, right? So this guy right here, you know, if you think about it, I'm going to just kind of map out in general terms, like this is how triprotic acid would work, okay? If, you know, the first acid H3A, okay, like phosphoric acid, like in this case, and then you lose an H, so that's HPO4 minus, you lose another H, and that's HPO4 2 minus, and you lose that final H, and that's PO4 3 minus. Okay, so yes, that's Ka1, that's Ka2, and that's Ka3. Okay, now for this one, it says the Kb for HPO4 2 minus is 1.6 times 10 to the negative 7. So I say to myself, okay, this guy, HPO4 2 minus is this guy. Okay, so, and the Kb is 1.6 times 10 to the negative 7th. Okay, so that means that that Kb came from basically solving for Kw over this Ka, right? Because this guy right here, HPO4 2 minus, is the conjugate base, right? Because it's Kb. So you have to look at what acid that conjugate base came from. So you go one step this way, okay? You add that H back on, okay? So it's basically, you know, the reason why this is the answer is because, you know, if you think about that math, 1 times 10 to the negative 14th, okay, divided by Ka2, 6.2 times 10 to the negative 8, the one they gave you. Well, if you guys think about it, this right here, that's going to work out pretty close to this number that we're going for, okay? So in other words, another way to look at it is, remember the Ka going in this direction, right, multiplied by the Kb going in the opposite direction. Okay, when you multiply those two, it will equal 10 to the negative 14th. Let me write it out that way. That might be a little clearer. So I'm just making myself a little more room here. It's really fun to erase, I have to be honest with you guys. Okay, so I'll just say that one more time to make sure you guys are clear. So like we're dealing with this guy and this guy, right? Okay, so when you go in this direction, that's Ka2. When you go in this direction, that's the Kb that came from Ka2, right? So basically, those two numbers multiplied equal Kw. So that would be 1.6 times 10 to the negative 7th times 6.2 times 10 to the negative 8th. Okay, if indeed those go together, that would have to equal 1.0 times 10 to the negative 14th. Okay, so I guess you guys can just do a little math and see if that works out. 6.2 times 1.6. You know, if you think about it, 6.2 times about, I mean, I think what would be the best estimate? Okay, so 1.6 times about 6. 6 times 6 is 36. 6, 7, 8, 9. So, I rounded this one to 6 instead of 6.2 to make the math a little bit easier. So it's 6 times 1.6 comes out to around 10 or 1, okay? So that, and if you guys add these together, -7 plus -8 is -15, okay? But if it's 10 times 10 to the -15th, if I do proper scientific notation, that's really 1 times 10 to the -14. Okay, so long story short, these two numbers go together. This is the KB that came from this KA, because when multiplied, it's pretty close to 1.0 times 10 to the -14. So, right, if this is the KA that came from this KB, that's the answer, okay? That's the answer for that one. Pretty tough question, like actually really tough question. So I guess, I really think it's like the only answer it could be, because these two, even if you weren't too super comfortable with that math, if they weren't somehow related, if they weren't related by Ka times Kb equals 1.0 times 10 to the -14th, these exponents would be way different, okay? Like this would be like to the -3rd or something like that, okay? And that in no way, shape, or form, when you add those exponents together, are you getting close to Kw? You know what I mean? If you multiplied them. So you guys are asking me some great questions. That was kind of a long answer for that question. Just a tough one, okay? So what can you guys take out of that? I think the most important thing in general, okay, is for all these problems, when you're given a problem, you just got to make sure you're using the right Ka value, or using Kb as needed. Okay, so I would say I like this question, but you know what question I like even better is probably ones like kind of near the end, like 23 is a really good one. Yeah, I think there was one other one. We'll see if it pops up, but even what you guys are gonna, if you saw on the quiz today, or you're gonna see on the quiz tomorrow if you haven't taken. Okay, so that was a long answer to that question. If you have a follow-up question, type it in the chat, okay? Because I'd love to hear from you. So that's number 12. I thought when you said number 12, you were referring to questions like 14, 15, 16. And I'll just throw that out there, folks. 14, 15, 16, please promise me you can make sure you can do that kind of math. Okay, those are like basic questions. Well, and acidic, okay? Just being funny there. So let me know if you need help with those. Let's see what else we got here. pH exchanges. How is pH scale affected by change in temperature? Okay, so that's a great question. pH is definitely affected by temperature, okay? But someone did ask something about number 12. Are we going to see something like number 12 on the test? Probably not, because I think that was asking a lot, but now that you, bottom line, it was too original of a question. Like I can't give it to you again because I just can't think of a way that I could really rewrite that. Okay, so it's just such a standalone question. So I'm glad you guys experienced it. I think you should know that Ka times Kb equals Kw, but yeah, probably not. Okay. All right, so this one, going back to water dissociating, right? What you guys will notice is like, I'll just give you some made up numbers. Actually, I also don't like the red, so I'm gonna switch. So let's say you're at 4, and I'm making up numbers, folks. Okay, so don't hold. Okay, are you kidding me? Like, what is that thing? Sorry, where did my pen go? There we go. So let's say at 40 degrees, Kw is like 3.1 times 10 to the -14th. At 25, Kw is, of course, 1.0 times 10 to the -14th. And let's just say at 11 degrees, I don't know, Kw is going to be like 7.2 times 10 to the -15th. So that would be like pretty common pattern, okay? And of course, Kw is the K value that goes with this dissociation, okay? So what do you guys see happening here? As temperature goes up, what's happening to Kw? Okay, so if we go from 11 to 25 to 40, okay, Kw also goes up, okay? So the first thing I might ask is, what does that mean? Is this reaction the auto ionization of water, is it exothermic or endothermic? So what side is the energy on? Okay, so I'm going to erase this real quick. So the energy can be on this side, endothermic, or the energy can be on this side, exothermic. So which one supports this data? Okay, so hopefully in the comfort of your homes, you guys are yelling, it's endothermic. Okay, because as temp goes up, that means you're adding more energy. KW is going up. And anytime K, I don't care what kind of K, is getting bigger, that means you're shifting more in the forward direction. Okay, so this supports that auto ionization of water is exothermic. Okay, so that's good. That's kind of a little bonus. Okay, now when you do shift forward, that means you're making more H plus and more OH minus. So just keep in mind that, you know, if it's a neutral solution, okay, then your H plus and your OH minus, they're basically in a 1-to-1 ratio, XX, they're going to be equal. So I know in my classes today, we talked about the fact that neutral is defined as when the H plus and the OH minus are equal, okay? Now, pH is a whole different thing. So what would happen to pH? So we can actually solve for that. So like these examples, let's say at 40 degrees, can you tell me what neutral would be? Okay, so we got X and X, right? That's your ice table, okay? So if you want to solve, it would be X squared equals 3.1 times 10 to the negative 14th. Okay, so to solve for that, okay, you guys would definitely just go ahead and take the square root of both sides. Okay, and what would X be? Okay, you might say to yourself, ooh, square root of 3.1, are you kidding me? I mean, you know, the square root of 4 is 2, okay? You know, the square root of 1 is 1. They kind of know it's a number between like 1 and 2, but who knows what it is. And guess what? Without a calculator, nobody's going to care. So I'll just make up a number. I know it's between 1 and 2, so I'll just say, you know, 1.3. I did make that up. I'm not calculating it, okay? I'll say it's 1.3, okay? And then if you take the square root of an exponent, that just means you cut it in half. So it's going to be, let's say, 1.3, that's an, you know, a round sign, 1.3 times 10 to the negative 7. Could you predict what kind of pH would that be? Okay. And you guys, the truth of it is, you know, without a calculator, you just need a range. Okay. So obviously it's pretty close to 7. Okay. But would it be a little more acidic compared to 7, or would it be like a higher pH compared to 7? Okay. And I know I talked about this in my classes, not my 6th bell. We'll get to you guys tomorrow. But this number right here, 1.3, is bigger than 1.0 times 10 to the negative 7. So if you know that this is pH 7, then this guy has to be pH less than 7. So it's going to be pH 6 point something, like let's say 6.8. Okay, I don't know what it is, but on no calc multiple choice, there's only going to be one choice in the 6 range. Okay, and I'm going to pick it. Okay, so bottom line is if you're at 40 degrees, okay, the pH for your neutral solution is going to be 6 point something. I'm saying 6.8. I didn't actually calculate. Okay, at 25 degrees, right, the pH of course is 7 because that's sort of your neutral standard water. Okay, and then what about this guy? Okay, so if it's 7.2 times 10 to the negative 15th, okay, well, if you take the square root of that, what kind of number would you get? I think you guys kind of see the trend here. Okay, but just for the fun of it, you know, this one seems extra awkward, but it's really not. Okay, so if I went ahead and tried to solve for that, I would say, oh, x squared 7.2 times 10 to the negative 15th. Take the square root. Okay, well, again, square root of 7, I don't know. I know the square root of 9 is 3 and square root of 4 is 2. So I guess it's between, you know, 2 and 3. Okay, so it's probably 2 point something, whatever. I'll say 2.3. And then you guys, even though that's an odd number, I can say to the negative 7.5. That's fine. Okay, but how does that number strike you? Okay, so is this number, again, compared to 1.0 times 10 to the negative 7th, is this number more or less H plus? And just remember that this guy is on its way to the negative 8th, right? Okay, so it's between the negative 7th and negative 8th. So what kind of pH would you get? Okay, so it's bigger than 1.0 times 10 to the negative 8th, but smaller than this guy. Okay, so guess what? okay, it's going to be in the pH range of 7.1. Okay, so you guys can sort of see the trend. We'll just say 7.3 again. I'm not calculating. Okay, I just want you guys to get used to sort of estimating, right? Okay, we're taking an assessment with no calculator. Okay, so what you guys can see happening with the pH is that, yeah, okay, as you lower the temp, which is what we're doing here, at 40 degrees, neutral would be at a pH of 6 point something. Okay, because at a higher temp, it went more in the forward direction. So you had more H plus and more OH minus, as it turns out, but the pH is in the 6 range. And then at 25, of course, neutral is pH 7. And then at 11, at a colder temperature, okay, then it's going less in the forward direction. So you have less H plus. So it's basically a pH higher than 7, okay, which means less H plus. So hopefully that helps you guys a little bit. Okay, I'm gonna see where you guys are. Okay, that's a great question. Okay, so that's the auto-ionization of water. And while we're at it, I see someone asked, could you go over the dissociation reaction for a neutral salt? Okay, you guys just remember, if it's a neutral salt, then guess what? The cation is not hydrolyzing, the anion is not hydrolyzing. And if it's not hydrolyzing, it's basically a spectator. So take a neutral salt, like salt water, okay? If the Na plus and the Cl minus aren't hydrolyzing, what's creating the H plus? Well, it would actually be this reaction. So that's you know, if it's a neutral salt, the only thing there is water breaking up into H plus and H minus, okay? And that's why, you know, that solution has a pH of 7, let's say, okay? So it's coming from the auto-ionization of water, okay? All right, and take home message, I think you guys got this loud and clear that, yes, depending on the temperature, you could have, the pH would not be 7, okay? The pH, you would have a new neutral, if you will, okay? And take home message is, as you increase temp, actually the pH of neutral water goes down, okay? You know, into the 6 range, okay? If you lower the temp, then the pH is above 7, okay? Because there's less H plus. All right, whew. You guys are asking me some great questions, so I feel like I'm giving these little monologues. Okay, let's see what else we got. Let's see. So what did owl mean by major species? And we have to do anything on the test? That's a great question. Major species, I think the way you'll see it phrased more often than that is major species is just, you know, what in that solution has the greatest concentration, okay? I can give you guys an example of that you guys might like. Let's see. How about, have you guys thought much about diprotic acids lately? I'll combine that idea with something about diprotic acids that I want you guys to remember, okay? Because you are hanging out with me on this lovely Tuesday evening. Let me come up with a diprotic acid. I'm looking at my yellow sheet here. How about ascorbic acid? Ascorbic acid. $100 if you guys know where you can find some ascorbic acid at your house. Anybody know? I got $100, I promise. So ascorbic acid, oranges. All right, good job. Yes, ascorbic acid is actually the chemical name for vitamin C. So anything that maybe even take, like, you know, chew on ascorbic acid like hard candy or something. All right, so nonetheless, ascorbic acid looks like this. H2C6, H6O6. Okay, it is a diprotic acid. Okay, and I will tell you, Ka1 is equal to 7.9 times 10 to the negative 5th. And Ka2, you know what? I keep saying that I don't like the red color, but yet here I am using the red marker again, okay? Ka2 for ascorbic acid, 1.6 times 10 to the negative 12. Okay, so I'm gonna erase something real quick here. You guys ready for this problem? It's gonna combine a couple things. Not sure why I erased that, mainly because I want to change the color. A 1.1 molar ascorbic acid solution. I want you to determine the pH. Okay, and I want you to calculate I'll call it this. Where's this ascorbic acid? C2 or C6, H6, O6, 2 minus. Ooh, guess what? Here's the fun part I want you guys to do without a calculator. Woo, not a calculator, what? Yes, you guys can, and for your pH, I'm gonna be super nice. I'm gonna give you choices, okay? What are my choices? I gotta think about that for 1 second. I'm gonna say A is pH 3, B is pH 3.55, C is pH 2.55, and D is pH 10.55. Okay, so like I said, I know you guys are concerned about doing stuff without a calculator, so let's give it a try. This one, I think it can be done without a calculator. What I want to, and okay, when we talk about major species, we'll get to that too, I promise. Okay, but the thing about this, if you have an ascorbic acid solution, if you have a diprotic or polyprotic solution, I want you guys to remember what Ms. Schneider and I taught you. Okay, it's an ice table. It's an ice table and it's diprotic. That means you get rid of the first H, then you get rid of the second H. So theoretically, you should have to do 2 ice tables. Okay, but this is a no calculator problem. Who's got time to do 2 ice tables? Okay, and Ms. Schneider and I, we showed you that really you don't need to do 2 ice tables. Okay, so let's just do that. Okay, and while we're talking about this, my next question after this is going to be, if you had a solution of ascorbic acid, what would be the species with the greatest ion concentration? Okay, so we'll come back to that in a minute. Okay, so I'm going to take my ascorbic acid. I'm going to rip off 1 H at a time. Okay, C6, H6, O6 minus. Okay, I'm going to set up an ice table. 0.1 molar, 0, 0, minus X plus X plus X. And I'm going to solve. Okay, so Ka1, 7.9 times 10 to the negative 5th. Okay, X squared over 0.10 minus X. Whoops. Okay. Do you guys think that you were okay to get rid of the minus X? This guy's on 10 to the minus 5th. Okay, so of course it's no calculator, so we will definitely get rid of that minus X. Okay, it's definitely small enough. Okay, so let's go ahead and solve. All right, so first thing, you got to take 0.1, right, and multiply it by both sides. Okay, I will promise you, when you multiply something by 0.1, that's like taking 10% of it, right? Okay, so whatever this exponent is, if it's minus 5 right now, when you multiply by 0.1, it's going to become minus 6. Okay, it's going to be 1 step lower. Okay, so I'm running out of space a little bit here. So let me just make a little bit more room. I'm going to get rid of the ice table, if you guys don't mind. Okay, so this is going to become 7. Oh my goodness, there's that red again. 7.9 times 10 to the negative 6 equals X squared. So you guys understand that. And then we're going to take the square root of both sides. Okay. Now, again, what's the square root of 7.9? Well, you know, square root of 9 is 3, so that's pretty close. So again, you know, it's a number between 2 and 3. So I'll just say, I don't know, 2.8. How does that sound? And then when you take the square root of this exponent, that's going to be times 10 to the minus 3rd. Okay. You guys see how easy that is? So that's going to be equal to my H plus. Okay. Now, here's the thing. What I really hope you remembered about diprotic acids is that is the H plus from the first dissociation, right? Okay, if you know anything about diprotic or polyprotic acids, if you write out pulling off the second H, the Ka value is much smaller, right? 10 to the minus 12. You're not going to get a significant amount of additional H plus from that second dissociation. So what Ms. Schneider and I taught you is you can basically use the H plus from the first ice table. The second dissociation is not going to contribute very much. Okay, so here's the fun part. And you guys take the negative log of that. Okay, so pH negative log of 2.8 times 10 to the minus 3rd. Okay, so try the techniques that we've been learning. Okay, obviously, you know, if you take the negative log of 2.8 times 10 to the minus 3rd, it's close to 3. Okay, but I hope that you guys realize it can't be 3. Okay, so basically, is it a pH a little greater than 3 or is it a pH a little lower than 3? And guys, it's just the same old message. And I'll say it this way to be real simple. Whatever that exponent is, I am telling you, okay, that the negative log of it is going to be in the next lower pH unit. Okay, so minus third will go down to 2 point something. Okay, minus eighth will go down to 7 point something. Okay, minus 11th will go down to 10 point something. Okay, so that's how it works. Okay, so bottom line is 2.8 times 10 to the negative third is more H plus than 1.0 times 10 to the negative third. So if 1.0 times 10 to the negative third is pH 3, this has to be more acidic. Okay, it has to be more H plus. Okay, so C is the correct answer. See how easy that was. Okay, now for this next part, okay, I could give you multiple choice, but guess what? I think you know the answer. Okay, and again, I'm not going to go through how we know this, but if you go back when Schneider and I taught you about diprotic acids, we told you that the concentration of the second conjugate for a diprotic acid will always automatically be equal to Ka2. It just is. Go back and look at it and prove it to yourself. You guys will see some math magic happens as you go from the first istable to the second istable, and there it is. So the concentration of C6H6O6 2 minus the second conjugate after you lost the first H, after you lost the second H, will be equal to Ka2. So you guys see that seemed like a really hard question, but it was actually quite doable. Okay, now I did promise you that I would tie this to major species. So here's my next question. Okay, given this acid, can you guys basically tell me if you had a solution of ascorbic acid, what species would make up the greatest concentration? And I'll give you guys some choices. So if you think about it, you know, and to be lazy, okay, I'm going to take ascorbic acid. Whoops, it is diprotic, right? I'm going to just say H2A, okay, and that could represent any diprotic acid, ascorbic, whatever, doesn't matter, okay? And just remember, okay, you break off an H, and then you make this conjugate base. That's the first conjugate base. You break off another H, and you make the final conjugate base, okay? So these are basically your choices, okay? You have 1, 2, 3, whoops, that's H plus, 4, and then I'll add to it OH minus. We'll make that 5. What do you guys, could you guys tell me what would make the greatest concentration in the solution? So if I was to look at a beaker of ascorbic acid, 1, 2, 3, 4, 5, what would I mostly see? What would have the greatest ion concentration? And I want you guys to think about it. Okay, so like on a multiple choice test, you know, if this was choice A, this was choice B, choice C, choice D, choice E, which one of those species would make up the greatest concentration in ascorbic acid? Okay, and guess what? Okay, the answer might be a little bit surprising to you, but it's actually the original acid, H2A. This guy right here would make up the greatest concentration, because what I want you guys to remember is that Ka value. For Ka1, 10 to the minus fifth. So guess what? This first dissociation, it does go in the forward direction, but not very much, okay? So if you had 1,000 ascorbic acids, I mean, gosh, not even 10 of them, okay, would break up into H plus and the conjugate base. Do you guys see what I'm saying? Okay, so gosh, the original acid H2O will make up the greatest concentration. Now then, let's see, what about, you got this guy and this guy. When H2A breaks up, you get one of these and you get one of these. They're in a 1-to-1 ratio, but you also get a little bit of an additional H plus than this guy. So I'm going to say H plus or hydronium will be the next highest concentration. By just a little bit, will it be greater than this guy? Okay, and then of course, you know, as you keep pulling off the H's, it gets harder and harder and harder. So you're even going to have less of this, because by the time you get rid of the second H, that's really not happening very much. Okay, so then A2 minus would be next. And then, you know, major species, this is the major species. Okay, in terms of like minor species, you know, what's the most minor species is, you know, I don't care what the solution is. If you always have H plus and OH minus present, but the more H plus you have, the less OH minus. Okay, so actually OH minus would come in as the dead lowest concentration. Okay, so I hope that helps. I think that's a more important skill. Okay, So I'm going to go back to the chat and kind of catch up. That was a great question. See what else you guys can add. Take home message there is just remember that concentration of the second conjugate is always equal to Ka2. Okay. And you can get the H plus from the first association. You don't really have to worry about the second association. Okay. Let's see. I see a request for 23. We can probably do that. There's a key. Okay, yes, there should be a key to the Fun with pH paper. If not, I will personally check to make sure that it's there and openable, but it should be there. Should be there. And I see someone said that they were able to find it. And okay, I see someone asked a question and answered their own question. Okay, so let's see. I think I'm looking at the chat. I don't think I missed anything, but you guys don't hesitate to type in the chat if you need further clarification on anything. Okay. All right. Hey, how are we doing on time? So you guys asked a question and I wanted to come back to it. So I got a real quick thing here. I was thinking about you guys and no calculator. This is a good question. Okay. You guys ready? I want to see if you guys can catch this one without a calculator. A weak base, 0.1 molar, we'll say. It's always 0.1 molar. A 0.1 molar weak base solution has a pH of 11. Calculate Kb. Okay, yeah, this is a good question. I just wanted to remind you that, we keep talking about, okay, we're going to do calculations without a calculator and all this stuff, but this one's, yeah, it's got that woven in, but it's more of a conceptual thing. I want to make sure that you guys catch up. So it says you got a weak base solution has a pH of 11. Calculate Kb. Okay. Now, if it were me, I would always start by, making sure I have a reaction in my head. Okay. So let's see. We got this base. Okay. Going back to our earlier discussion, it's definitely a Bronsted-Lowry base, if you will, because this weak base is going to accept hydrogen. Okay. We're going to make Hb plus. Okay, that would be the conjugate acid, right? And then what's left of water is OH minus. Okay, so we're making hydroxide, so that supports that. Okay, a Kb would go with this. All right, so it's basically an ice table, right? You got 0.1 molar, 0, 0. I think you guys see where this is going here. Okay, but the thing is you know what X is because it says that it's a pH of 11. Okay, and anytime I give you the pH of the solution, that's its equilibrium concentration basically. So it's a pH of 11. Okay, so I say to myself, okay, well, how can I solve for X? And this is where I want you guys to be careful because this is hydroxide. This is pH. So do I need pH or do I need POH? Okay, and I hope that you're yelling at the top of your lungs, POH. Okay, so for this problem, the POH would be 14 minus 11 would be 3. So the hydroxide would be 0.001 or 1 times 10 to the negative third. Okay, so that's actually your X. Okay, and if that's equal to the OH minus, that's also equal to the Hb plus. Okay, so you guys start to see how this comes together. So your Kb would be 0.001 squared, right? Because it's OH minus and Hb plus over 0.1 minus 0.001. Okay, can you guys solve that without a calculator? Okay, so 0.001 squared would be 1 times 10 to the negative 6th, right? So you add up those exponents, -3 plus -3. Okay, let me get rid of that for a second. Keep getting rid of our ice tables, that's okay. Making room, making room. Bye-bye, 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 bye-bye. Okay, so that would be on the top, 1 times 10 to the negative 6th, right? 10 to the minus third plus 10 to the minus third. Now 0.1 minus 0.01, so let's talk about that for a second, folks. Right now, 0.1 minus 0.001 is pretty much 0.1. But I tell you what, don't skip this, okay? Like if you can use a calculator like on the short answer, like make sure you do that, okay? Like if you know what this number is, there's no reason to cross stop, okay? In this case, I'm just trying to make the math easier. So I'm going to say it's about 0.1. But if it was on the short answer and I could use a calculator, I would use like what is that, 0.009 or 0.09 or whatever that is. Okay, I would actually calculate that out. Because sometimes with these types of problems, 0.1 minus this number, it makes a difference. Okay, so don't exclude that if you can use a calculator. Okay, so what would this give you? Now, I think for some of you, you're like, oh, that's super easy. 10 to the minus 6 divided by 0.1. I think it's either going to be 10 to the minus 7th or 10 to the minus 5th. Okay, but I could see getting confused about that. Okay. This is kind of the opposite of taking 10%. So 10% would make 10 to the minus 6 smaller if you're multiplying it. So if you're dividing it, it's going to do the opposite. Okay, so it is going to be 10 to the minus 5th. If you don't like that answer, I'll just remind you, I think scientific notation could be really helpful. This is 10 to the minus 6. This is 10 to the minus 1, right? Because you're moving over one spot. What do you do with those exponents? You subtract them. So minus 6 minus 1 is to the minus 5th. Okay, so the KB for this guy would be 1 times 10 to the minus 5th. All right, good. So my point here is please don't forget that, bases are based on hydroxide. Okay, so if I give you a pH, you do have to manipulate that. Okay, I can tell you so many cases where students get really crazy answers because they used pH instead of POH. Okay, kind of get rolling with this problem. So I hope that was a helpful one. When you guys were asking about math calculator, that came to mind. All right, I'm checking to see what else. All right, let's see, other questions. I'm looking at the chat, I'm not seeing anything. So if you did type something, I'm not seeing it. So type it again, okay? Make sure, remember, I can't check the chat on this computer I have in front of me. I check it on my other computer. Okay, while I'm thinking about it, I got a couple other things I'll share with you guys. If you guys are still there, are you still there? Okay, I see I have 44 participants. I love it. Let's see. Ooh, I know we're kind of running out of time. I have so many other ones. Somebody asked about 23, and boy, now I'm a little bit bored. You know what? I'll do something like that. I got a couple things to give you guys. We'll come back to that, I promise. How about this? So that's a little messy. I'm trying to make, you guys don't understand. My screen has so many like tabs open and stuff. I don't have any room. I'm going to ask you guys to circle. Whoops, the lowest pH. Okay, so I'm going to give you guys some interesting ones. Circle the lowest pH. That means the most acidic or the most H+. How about a barium oxide solution versus phosphorus tetroxide solution? Okay, so those two guys dissolved in water. Okay, now this is going a little bit back into the archives, but folks, this is definitely an acid-base thing here, so it's very appropriate for this chapter. Okay, barium oxide versus phosphorus oxide or tetraphosphorus decoxide. So it's basically a metal oxide and a non-metal oxide. Okay, and that should impart some knowledge in your head. Okay, non-metal oxides dissolve in water to make acids. Okay, metal oxides dissolve in water to produce base. You guys should be able to write a reaction for each one of those too. Like barium oxide plus water, what's it make? Okay, it makes barium hydroxide. Okay, and you guys can balance that out. Okay, and non-metal oxides plus water dissolve to make acids. Okay, now this one I specifically gave you guys a weird one. I could have done CO2, which is so easy. It makes carbonic acid. This one, I mean, you got to be a little creative. What acid are you going to make out of hydrogen, phosphorus, and oxygen? Hopefully the first thing that comes to mind is phosphoric acid. And that would be right. Okay, so you guys can go ahead and balance it. But yes, non-metal oxides dissolve in water to make some kind of oxy acid that's familiar to you. Okay, so that's a good one. So that was, we'll call that number one. Number two, how about H3PO4, since we had that in our mind, versus H3PO4, H3PO3, sorry. So for strengths of acids, right? We talked about that last week. Okay. What do you guys think? More O's or less O's? Which one's going to be more acidic? Hopefully you guys said more O's. Okay. And hopefully you guys have some reasons for why. Okay. That more O's means more electronegative things, pulling the electron density away, weakening the bond to the acidic hydrogen, making it a stronger acid. So you guys might want to review that. I got a couple of these. Ooh, how about HCl or H2SO4? Which one's going to be more acidic, a lower pH? Okay. And I hope what you guys are thinking here is that, ooh, let's see, H plus, Cl minus, but this guy is diprotic. Okay. So guess what? H2SO4, if they're equal molarities, okay, you're always going to get more H plus from a diprotic acid, because you're going to get all of the first H coming off because it's a strong acid, and then you're going to get some of the second H coming off. Okay. But like, let's say if this was 0.1 molar, what would be the H plus concentration of this guy? Okay. And I'll tell you, it will not be 0.2 molar. Okay. Because guess what? That's my whole point. You will get rid of the first H completely, but you're just going to get rid of a little bit of the second H. Okay. So maybe 0.11 molar would be a better answer. Okay. So you're going to get the first H and then a little bit of the additional H. Okay, this is fun. Okay, oh, I know. You guys are asking about the 23. How about this? This one's kind of related. Sodium carbonate or sodium nitrate. Which one? I was asking which one's more acidic, right? Now in this case, of course, Na plus, neutral cation, right? Because it's a low charge big metal, so it's not going to hydrolyze. Na plus is not going to hydrolyze. Okay, so it comes down to those conjugate bases. So you got CO3 2 minus and you got NO2 minus. Okay, which one is going to produce more OH, less OH minus, I should really say. We're going to pick the less basic one. Okay, the less basic one. Okay, the one with the pH closer to 7. Okay. So you guys, this was my point for carbonate. Okay, obviously you're going to need a Kb value. Okay, it is a conjugate base from a weak acid. Okay, so to get that Kb, I'm going to take Kw, which is 10 to the minus 14th, and I'm going to divide it by Ka that goes with that. But that is a big question, and this will help you with number 23. That's a carbonate. Okay, if this guy is going to hydrolyze, it's going to gain that H, HCO3 minus plus OH minus. So this is the conjugate base. This is the acid it came from. Okay, does this acid go with Ka1 or Ka2? Okay, well, you know, kind of using general diprotic acid, you lose the first H, right? And then you lose the second H. Okay, Ka1, Ka2. So which one are we dealing with here? Okay, so this conjugate base came from this acid. That's this guy right here. Okay, and this is the conjugate base that came from that acid. So long story short, it's Ka2. So for carbonic acid, CO3 minus, I look up carbonic acid, this Ka2 is 5.6 times 10 to the negative 11. Mostly I'm just going to focus on those exponents and estimate that to be about negative 14th minus a minus 11th, 10 to the minus 4th. Okay, and then can you guys do the same thing for this guy? So, okay. Oh my gosh, so many colors. I love it. I'm sorry. 10 to the minus 14th. Now this one's easy because nitrite, okay, that's coming from nitrous acid. That's just monoprotic, so I don't have to worry about making a choice here. I'm just going to look up nitrous acid, 4.0 times 10 to the negative 4th. So I think we got a clear winner here. So when I subtract those, that's 10 to the minus 10. Okay, so guess what? Larger Kb means more hydroxide, right? Okay, so this guy right here, that's a larger Kb. So that one's going to be more basic. So this guy's our winner because this guy's going to be less basic, closer to 7. In other words, more acidic. It's going to have more H plus. Okay, you guys see? So long story short, age-old concept, okay, that the weaker acid produces the stronger conjugate base. This guy, times 10 to the negative 11th, was a weaker acid. So it did indeed produce a stronger conjugate base. Okay, CO3 2 minus 4 OH. Ooh, that was a good one. Ooh, I got another one. Let me check the whatchamacallit, the chat. I gotta ask you this one. I forgot it. It was in my head. Hold on, it's coming to me. I do like this purple. How about aluminum nitrate? Let's see, is there no. How about cadmium nitrate? Cadmium nitrate, cadmium nitrate. I like that. Nitrate, and we've got one more, zinc nitrate. Can you guys put those in order? From most acidic, lowest pH, to least acidic, okay? All right, so what do you guys see here? So hopefully you guys notice you got some metals, okay? And metals can hydrolyze depending on the charge and the size. So we got aluminum +3, we got cadmium +2, cadmium +2, and zinc +2. All right, so who's gonna be the clear winner here? Most acidic. Okay, hopefully you're yelling that aluminum nitrate would win, okay, because it's a +3 charge. Folks, please make sure you can write out these reactions. So aluminum, how does aluminum +3 hydrolyze? Well, first, it has to get hydrated first. Okay, so that means it's going to get surrounded by waters. Okay, then the hydrated form of aluminum can hydrolyze. So now it's going to behave like an acid, okay? And basically we're going to lose an H. So 5 of the waters will stay intact, but 1 of the waters lost its H. So it's just going to be OH minus. And this whole rascally thing now has a 2+ charge because you lost that H+, okay? And you have this OH minus, okay? And just remember that looks kind of funny right there. The whole story with that, why does that occur? Is we just, aluminum having that big +3 charge, it can attract these waters. We talked about that. It's kind of a Lewis acid base thing. Okay, it attracts those waters, and being the +3 charge that it is, it does a really good job attracting the water. Okay, so when that water gets, when you pull on the oxygen of the water, that weakens this bond. Okay, and then the little He falls off. Okay, and the little He falls off, that means it's a stronger acid. Okay. So yes, make sure you guys do that process. So aluminum, numero number 1, okay, most acidic. Now, these are all +2s. Now between cadmium and zinc, you look at your periodic table, zinc is in like the 3rd period, cadmium is directly below zinc, okay? So if I had to pick between these, zinc is a smaller atom with a +2 charge versus cadmium. So zinc has a +2 charge, but because it's smaller, it's going to hydrolyze more than another 2+ charge is bigger. So zinc nitrate will be 2nd. Okay. Now between my cadmiums, we have cadmium nitrate and cadmium nitrate. Now, hopefully you guys concluded that nitrate is a conjugate base of a strong acid. So that guy is not going to hydrolyze, neutral. Okay. It's a spectator. But this guy is a conjugate base of a weak acid. So it will hydrolyze. So bottom line is, since this is going to make an acidic solution and this is going to make a basic solution, boy, some of that H+ and OH minus is going to cancel each other out. So this guy is definitely going to be 4th place. Okay, because you would have to look up the Kb for nitrite versus the Ka for cadmium that I don't know offhand. Okay, to see, it might even be a basic solution. Okay, if the Kb for nitrate is greater than the Ka for cadmium, then it would actually be above 7. So what do you think? Good? Good? Yeah? Okay, let's see. Somebody asked, why do you always get 6 waters? Let me tell you, okay, that is just sort of a general, pattern that we see, that whatever the charge is, you just double that to get the waters, okay? And, it's kind of a gray area, but I think it just works to give us the idea that the bigger the charge, the more that guy attracts waters, okay? So the more hydrated it gets, okay? wait, why is CD solution more acidic? I missed that. Oh, no problem. So with cadmium versus zinc, they're both +2 charges, okay? So they might or might not hydrolyze, but according, if you think about the periodic table, look at the periodic table, zinc is all the way over to the right, okay? Let me just draw a little periodic table. So this is a nice, ooh, look at that, so pretty. Okay, so here's our little periodic table. It's actually that's probably the best thing I've drawn all day. So there's zinc, okay? I would write ZN in there if I could. Cadmium is right here, okay? Now, here's our +2 metals, okay? This is beryllium, this is magnesium, definitely hydrolyzed because they're small +2 metals. Here's calcium. Calcium's kind of like, it might not hydrolyze because it's big. Okay, and these two guys, strontium and barium, definitely don't hydrolyze because their +2 charges are too big. Okay, they don't have a good charge density. Okay, now as you go across the periodic table, size actually gets smaller. So zinc 2+ is actually smaller than calcium 2+. Okay, because as you go this way, they get smaller. So zinc is definitely going to hydrolyze. Now cadmium, it's a little bit bigger. It might be considered sort of neutral, but in this particular context, that wasn't really the point. It was just ranking that cadmium 2+ would hydrolyze less than zinc 2+. Okay, it might even be considered a neutral ion. Like I said, it's kind of a gray area. It's just comparison. Okay, so hopefully that helps. All right, what else? Okay, well, guess what? I'll get. I'm looking over some of my notes. I mean, I gave you guys some good ones. I really did. Yeah, I'll give you guys one more thing to think about. We talked about HCl versus H2SO4, and like H2SO4 would have a little more H+ than HCl. What about on the strong base side? Some of you guys missed this on that quiz that we took like a week or so ago, that if you had like a 0.1 molar NaOH solution, it would basically, you guys can do that without a calculator. Okay, what would be the OH minus? Well, it's going to dissociate 100%. So the OH minus would also be 0.1 molar. So what would be the POH, right? If you take the negative log of that, the exponent, of course, is 1. So what would be the pH? It'd be 13. Do you agree? Okay, so what if you also had a 0.1 molar solution of barium hydroxide? Well, here's the catch. Okay, you get 2 hydroxides per every barium hydroxide. So it would be 0.2 molar. Yeah. Okay, now you guys got to do some math on a calculator. What would be the POH for a 0.1 molar solution? Okay, well, obviously, if you guys think about it, the negative log of 0.1, like this guy, was pH 1. Okay, so 0.2 though is in between 0.1 and 1, like the whole number 1. You guys agree? This is going to feel a little weird. What's the negative log of 1? Okay, well, that's actually 0. Okay, so this guy's POH is going to lie. It's going to be basically point something. Okay, it's going to be a number between 0 and 1, like 0.4 or 0.6 or something. Okay, so then when you subtract from 14, long story short, okay, if this guy is a pH 13, this guy is more basic, right? It's got more OH minus. So it's going to be 13 point something, okay? Because you got more OH minus, okay? So you guys can do that kind of stuff without a calculator. So like I said, if you think about it mathematically, if the negative log of 0.2 is like 0.6, let's say, then what's 14 minus 0.6? Okay, it would be 13.4, right? It's 13 point something. That is representing more OH minus than what was here. Ooh, that was a good one. Okay, I am looking at the chat. Folks, and this is your last chance. I went on a rant. I went on an acid base, like just total monologue there. Okay, I just kind of went off the grid. So please make sure I answered your questions. Are you sure? Does anyone want to see what we had for dinner this week? Whoops, can you guys see? It's like the menu. goulash. Do you guys eat goulash? I don't know. It was really delicious. My husband made it. Okay. I made the salad. What else? You guys have any questions? When do we decide that calcium doesn't? Okay, let me tell you, calcium, that's like on the fence. Okay. I don't know if calcium hydrolyzes or not, honestly. It might be slightly acidic. Okay. I'm going to say it's just like kind of on the fence. All right. Well, I appreciate it. I see someone yelled out a thank you. It's my pleasure. Okay. All right. But folks, you know what? If you still have questions, please promise me you'll ask them. Okay. Because I'm telling you, the only dumb question is the one you don't ask. Okay. And this stuff is tough. So believe me, I don't care if it's from the first day we learned anything. Okay. Actually, it's those questions that really throw people off. So don't hesitate to ask, even if it seems like the simplest, dumbest thing. It's not, I promise. Just make sure you guys ask. We have connect time tomorrow too. So, if you guys want to sneak into Miss Schneider or my room, I'd love to answer questions. All right. Hey, I'll stick back a little bit if you just had that one question that you just want to ask me. I'll just stick on for a little bit. But otherwise, you guys have a great night, and I hope the Comets are winning. Princeton, that's pretty awesome. All right, we'll see you guys tomorrow. Have a good night.
One question that I didn't get to type.
Okay.
Why would an element get smaller as you went on to the right of the periodic table? I feel like it would get bigger because wouldn't it have more protons, more electrons?